Hi, for this video we will be discussing some of the applications of integral calculus. Solving force due to fluid pressure. Pressure is defined as the force per unit of area over the surface of a body, and then in general, the pressure is proportional to the depth of the object in the liquid. That's why in here you can see pressure P on an object at depth H in a liquid is pressure is W times H, where W is the density or sometimes called weight density of the liquid per unit of volume. Here you can see some of the common weight densities of fluids in terms of pounds per cubic foot. So in this figure, what you can see is that pressure varies at different depths, where at this point, P1 would be the same, P2 would be the same, no matter the orientation of the object. In this slide, fluid force due to liquid pressure is the force per unit area exerted by the liquid on the plate. And it has a formula, pressure is equal to force over area, or if we derive and then isolate F is equal to P times A. And then we have to take note from equation number 1 earlier that P is the weight density times the height. Therefore, this one would have a formula of WH times A. So when calculating the fluid pressure, you can use an important physical law called Pascal's principle, named after the French mathematician Blaise Pascal. Pascal's principle states that the pressure exerted by a fluid at depth h is transmitted equally in all directions. Just like what I said, as you can see in here in this figure, at this depth h, the pressure would be the same no matter what the orientation of the solid is. Here it's inclined, here it's horizontal, here it's vertical, but then all the pressures at that point would be the same. So because fluid pressure is given in terms of force per unit area, the fluid force on a submerged horizontal surface of area A is P times A. So let's try solving. Find the fluid force on a rectangular metal sheet measuring 3 feet by 4 feet that is submerged in 6 feet of water, just like this one. So how can we solve this? You're asked to solve for force. In the next slide, you can see pressure is density times height. And then the density of water is given to be 62.4 pounds per cubic foot multiplied by the height, which is 6 feet. And then that is just the pressure. But what's the area affected by that pressure? That's 3 by 4, so by 12 feet. So the total force is pressure times 12 feet. It would be 4492.8 pounds. This pounds is what you call pound force. But then in integral calculus, more often than not, we will be dealing with differential force, meaning the force or the area in here is not all the time equal and the force is not all the time constant. Therefore, dF is equal to WH dA. So the total force would then be the integral from A to B of ya minus yb, x right minus x left. I'll show this to you later on. And then times dy multiplied by the constant, which is the density. So let's try solving. Solve for the force acting on a rectangular slab 10 feet by 6 feet. If the slab is situated vertically such that the edge of the slab lies on the surface and that the slab is fully submerged 6 feet in the liquid, so use the density of the liquid as W. So let's just say in here, if I'll draw my X and Y axis, and let's just say I'll use my slab. Let's use another color. This one. This would then be my slab in here. One of the edges is lying on the surface, exactly on the surface. And then let's use this as the surface of the liquid, of the water, for example. So that is the surface of liquid. This is your y equals 0 or the x-axis. And then let's try to label whatever we have in here. This is 10 feet by 6 feet by 6 feet by 10 feet. So in order to solve for the force, we have to first have a representative element. So let's just say the representative element that I want to have here, I'll just draw it here, a horizontal element. So this would be the differential area. Okay, let's label. This one in here would then be my dy or your dh. In our case, let's just say dh. And then this would be the height or depth of liquid. The total length of liquid would be this one. This is the length. Therefore, if you're asked to solve for the total force acting on the body, what's the formula that we need to use? Formula, force is, let's bring out the constant W, integral from A to B of H dA. Therefore, the parts that we need are W, H, and then dA. For W, that's just constant. The height, it would come from the y-axis, which is the top of the liquid, up to any y value. So let's just say that's 0 minus y. Whereas for the differential area, the length is constant. It's always 10 times dh, or length times width. It so happened that your width is a dh. So here, it would then be 10 dy. And then what would be the limits? The limits would be what is the area submerged. Because the differential is area, it has to be what is the area submerged. The area will start from -6, this point, up to 0. Therefore, if I ask you what would be the force, just try solving. Force is W from -6 up to 0 of negative y 10 dy. So let's just bring out whatever we can bring out. Let's bring out negative 10w, negative 60 of y dy, negative 10w, y squared over 2 from negative 6 to 0, negative 10w, 0 minus, that's 36 over 2, that's 18. Therefore, 180 w force units, because we're not given any units. So it's this one. Let's try another one. Basically the same shape, a rectangle, but I'll just change the where it's located. If, for example, if I have, say, still the same shape, but then now what I will be doing is I'll try to put it in the middle, or let's just put the shape, the same shape, in the middle, but then a bit lower. Because some of you might say, can't we just take half of the force and then multiply it by 2? We can actually. So let's just try this. Let's select a representative element for the area that will be subjected. Now, in this case, it's still the same height. This is still at 6 by 10. 6 by 10. But then now, it is submerged. The top of the slab is submerged 2 feet below the surface of the liquid. So this is the surface of the liquid. Let's just write here, y equals 0. So if I ask you the height, it would be subjected to this height of liquid. And then this is your dh, which is actually dy, right? This would be, since we use this as the y-axis. Since we use that as a y-axis, we can see that this is 5 feet and 5 feet. And then here, the total would be 8 feet. So again, with the formula, F is equal to, let's bring out the constant, from A to B of H dA, the W, H, dA, and then the limits A and B. For W, we already know that that's constant. For H, we start from the surface of the liquid. It so happened that in here, it's 0, so that's 0, minus, it ends at any y value where the element is at. Now, dA, of course, that's length times width or length times height, whatever you're using. So in our case, the length is 5 times the height is dy. And then the limits, what's the area affected? It's from -8 up to -2 because this is from here, this point up to this point, the area submerged. Therefore, I can see that that's from -8 up until -2 only. However, let's look at the representative element. The representative element only represents half of the slab. So in order to solve for the force, the total force, my formula should be half of the force is equal to W from A to B. So that's from -8 up to -2. H is -y. And then dA is 5 dy. Again, let's bring out what we can bring out. So that's 2 times, let's bring out the 5. That's -10W from -8 to -2 of y dy. So this now becomes F. -10W y squared over 2 from -8 to -2. This is -10W. 4 divided by 2 is 2, minus 64 divided by 2 is 32. Therefore, -30 times -10 is 300 W force units. So again, I have to show here that it's F divided by 2 because I only considered half of the slab in that example. If I give you another example wherein I place my slab on the other side, let's use the same examples. Still 10 by 6, but then now, what I'll do is this. This is the surface of the liquid, and then that's 1 foot, and then only 5 feet is submerged. The total is still 6 feet. The total here is still 10 feet. So let's draw the representative element. The representative element would be a horizontal element. So this one. And then when you draw the height, it has to be only what is the affected area. So this is the height. It does not start from the top because the top is not submerged in the liquid. This one would be the dH. In our case, that's just dy. So let's start the formula. Let's rewrite the formula. W HdA from A up to B. So W H dA and then the limits. For the weight density, we use the W as the constant. For the height, it starts from the the x-axis, wherein y equals 0, so that's still 0 minus y. It does not change. dA, still, that's 10 feet, times dH, which is dy in our case, and then A and B. So the affected area, would be from -5 up to 0 only, because that one there, the one on top, is not affected anymore. So here, force would be W from negative 5 up to 0, negative y, 10 dy. So let's bring out what we can bring out. Negative 10W from negative 5 to 0 of y dy, negative 10W, y squared over 2 from negative 5 to 0, negative 10W, 0 minus 25 over 2. So 5 times 25 is 125 W force unit. So this is a total force acting on that slab, the immersed or the submerged slab. Now, it's easy because those are rectangular slabs. What if I gave you something else like a triangular slab? So let's say I'll use a slab that is isosceles. So this one is 6 feet by 6 feet. And then it's submerged in the liquid. And then one of the legs is on the surface of the liquid. That's y equals 0, or again, the x-axis in this case. Let's use this as our y-axis. All right. So the thing is, when we draw our element, we can see that this one would be the representative element. No problem with this. And then we need to have a height. That representative height would be this one, and then this would be dh. In our case, that's no dh or dw. So let's write the formula. Formula w integral of hda from a to b. So for w, we don't have a problem. For rw, we don't have a problem so far. We know that it's given as constant from the first example. The h, it's from 0 up to any y value. Again, no problem. 0 minus any y value that the yellow element reaches. The dA, you know that it is always length times width. But then, now the length is not constant. That is the problem. Because for my length, since length is not constant, it should be from the right, x of the right minus x of the left. The width, we don't have a problem. The thing is, what's the x of the right and x of the left? Let's look at this points. These points are 6, 0, and we can say that this is 0, negative 6. So let's solve for the equation of that line. Remember the slope? y2 minus y1 over x2 minus x1, or basically change in y over change in x. So 0 minus negative 6, 6 minus 0 is 6 over 6, which is 1. Now, let's pick one. I'll pick the positive one. Y minus y1 is equal to slope x minus x1. Remember this formula? Y minus y1 is equal to m x minus x1, the point slope form of the equation of the line. Therefore, the x1 would then be 6. So y equals x minus 6 is the equation of this line. However, when we look at the length of that element, the yellow, the right side of it touches that line, which has an equation of y equals x minus 6. But what we need is the x. So let's isolate the x. X would actually be y plus 6. Therefore, we write here y plus 6 minus, what's the left side? The left side ends here. X equals 0 because that's the y-axis. Therefore, L would just be y plus 6. What about the width? The width is actually just dH, or in our case, dy. There's no problem with that. That's the differential width. Now, if it's submerged, fully submerged up to a depth here at that point, 0, -6, I can see that A should be -6 and then B would be 0 because it's submerged up until here, surface. Therefore, this one would have a formula, -6 up to 0. The H now is -y. The dA would be L times W. L is y plus 6. W is dy. So let's distribute this first. -6, 0, -y squared. Let's bring out the negative. So that's negative W. So y squared plus 6y dy, negative W, that's y cubed over 3. And then plus 6y squared over 2, so 3y squared coming from -6 to 0. And then just solve for this one. Now, I'll give you another example. What if, just so that you get used to it, the same triangle, but then now it's submerged even further down. So this one would be, let's just say, 2 feet below. And then this is still the same, 6 feet by 6 feet. So the surface of the liquid would be here on top. And then let's draw the representative element. The representative element would be here, a rectangular element. Let's draw the height. It would be coming from the surface of the liquid, that's h. So this one would be dh. So it's important that we know the point. So let's just say this point and that point. This point would then be 6, but then it's below by 2. So 6, -2. And then this point here would be 0, -8. So if I ask you for the slope would still be the same. So -2 plus 8, 6 minus 0. So that's 6 over 6. It's 1. We just shifted it down, actually. So y minus y1 equals slope x minus x1. Therefore, x is equal to y plus 8 is the equation of the line, this one. X is y plus 8, or if you want, y equals x minus 8. All right, let's write the formulas. F W integral of h dA. So I'll just write the equations. I won't be solving anymore. Anyway, the solving part is easy. W, H, dA, and then the limits. W, it's constant. The height would be coming from the surface of the liquid, which is y equals 0. So that's 0 minus y. Unless we say that place the surface of the liquid here on the edge of the triangle. But then for now, let's place the liquid there. dA would be length times width. Your length is the length of the yellow rectangle. So length is x right minus x of the left. The x of the right is a y plus 8. It so happened that it ends at the y-axis, so that's minus 0. So all in all, W is dH, or that's just dy. Therefore, your dA, we can solve that. And then the limits, again, the affected area is from -8 up until -2. Therefore, if I were to write the formula, W constant from -8 up to -2, H is just -y, dA would be y plus 8 dy. All right? Now, last, if I give you another example, wherein I'd like to switch it up a bit. I'll make it like this instead. This is 6 feet below. And then the liquid, I'll place the liquid at a much higher location in here. And then I want you to place the x-axis in here. Therefore, y equals 0, and then this is the y-axis. So you're asked again to solve for the force. So maybe since it's isosceles, we can say that this one, let's complete this first. From here to here, the triangle, that's 12 feet. So this is the same as this one. So we can just take half of it. And then let's draw the height. The height would be from the surface of the water. It so happened that this one is y equals 2. That is your height. This one is your dH, or sometimes you want to call it dW. So let's give the points. This one is 0, -6. This one is 6, 0, just like earlier. Therefore, again, for that, the slope is just equal to 1. And then we already have the equation earlier. Or you can just choose any of the points. Y minus y1, so y plus 6 is the slope. X minus x1, I use the 0, -6. So this one, x would just be y plus 6 as the equation of my line. So x is y plus 6. So let's complete all the parts. W, H, dA. W is constant. H is from 2 minus y. It's not 0 anymore. And then dA would be length times width. It so happened that your length is right minus left. So x of the right minus x of the left. X of the right is x equals y plus 6. And again, the left side, if you want, you can use this on the left side. But then, since it's symmetric, what I did was divided it into 2. And then later on, I'll just multiply by 2 my answer. So it's easier to solve. And then the width is simply dh or just dy. And then what about my limits? My limits would be, what's the affected area? It's from -6 up to 0 only. Some might say it's up to 2. No, because there's no more slab in there. The slab is only up until this portion. So force over 2, because it's half, would then be W from -6 to 0 of H, which is 2 minus y. dA is y plus 6 minus 0, or simply y plus 6 dy. So that is the formula. Now that we understand it a bit more, a bit better, here, let's try this. A plate in the shape of a rectangle is submerged vertically in a tank of water, with the upper edge lying in the surface. If the width of the plate is 10 feet and the depth is 8 feet, find the force due to liquid pressure on one side of the plate. So if it's not stated, let's just say the weight density, let's just make it constant, just W. So this is the figure. So it's submerged. So the representative element here was stated to be this orange rectangle. It has a length x, any x value, and then it has a height or depth h. The thickness is dy. So height is 0 minus y, just like my examples earlier. And then for the solution, 0 minus y, it so happened that since here, the length is constant because it's 10 feet, and then we take half of it. That means x is equal to 5. So you can see here, that's 5 minus 0. But you have to take note that the force is divided by 2. And then the slab is submerged fully. So until a depth of -8. because in here you can see the whole slab is submerged from -8 up until the top, which is 0. So in here, the final answer is 320 W force units.